Hi, everyone. Good morning, good afternoon, good evening, and welcome to our AI Virtual Tech Talk series. Particularly a warm welcome if you haven't joined one of these before. And to everyone, actually, a very happy new year. I think we can still say that. It's the 25th of January. I hope you had a good break if you celebrated the new year and the festive break. Hope you had a restful time and enjoyed it. So we're back with our tech talks. We had one just 2 weeks ago from our AI ecosystem partner, Kixo. And we've got a fantastic tech talk lined up for you today from Reality AI, talking all about the art of segmenting real-time sensor data for tinyML applications. So it's great to have them joining us today. And it's great to have you joining us today. We're really, really excited. This is the place for anything to do with AI trends, technologies, and best practices from the world of ARM, speakers, and our ecosystem. So it's great to have you today. And we really encourage you to get involved in the conversation. So in addition to all the kind of chat and Q&A functionality, which I'll get to in a second on Zoom, you can, of course, tweet us. So you can go to Twitter and go to @ARMSoftwareDev and use the hashtag AIVTT. Give us a tweet. Let us know how you're finding the tech talks and get involved in the conversation. We'd love to hear from you. All of our prior talks are on our ARM Software Developers YouTube channel, so you can check those out. Oh, sorry, Jeff, you wouldn't mind just going back one slide? Thank you. And that's on our Software Dev YouTube channel. And you can also sign up for our next AI Tech Talk at arm.com/tech talks. All the slides, all the recording from today will be available hopefully by the end of play today, UK time, or within 24 hours or so. So do check out that and you'll be able to get access to all the slides, all the material, all the recordings from today straight after this tech talk. And there's a whole bunch of tech talks coming up, so let's check those out. We've got one in 2 weeks from our AI ecosystem partner, DeepLight, talking about their faster time to production for computer vision AI on ARM. We then have the first in a really exciting installment of ARM ML quarterly research specials. So if you have particular interest in the latest from our ML research team, they're going to be talking about federated learning and a particular paper they did on federated learning. So do check that out. That promises to be a really exciting tech talk in about a month's time. Followed up by a tech talk from our AI ecosystem partner, Plumerai. And this is just a small sample. We've got a bunch more scheduled for the rest of the year. And as I said, this is the place to be for AI trends, technologies, and best practices from the world of ARM and speakers from ARM and our partner ecosystem. And as I mentioned, we've got Reality AI here today. We've got Dr. Jeff Siraki today, co-founder and CTO of Reality AI, joining us and presenting on this topic. So Jeff, I'm going to ask you to get your camera on, turn on your mic, and the floor is yours. It'd be great for you to talk to our audience today about this. So over to you. And just before I do, actually, don't forget to pop your questions in the Q&A box. For those of you who haven't used Zoom before, it's in the menu bar at the bottom. So get your questions in for Jeff and for Stuart as well, Stuart Pfeffer from Reality AI. Over to you, Jeff. Apologies.
Great. Thanks, Tobias. I'm assuming you're hearing me just fine there. Yep, I am Jeff Siraki, co-founder and CTO of Reality AI. I bill myself as an extremely applied mathematician because I like to make math do things in the real world. I've been working a while now in modern signal processing combined with machine learning. And that, not coincidentally, is what Reality AI also focuses on. I'm going to talk today about the art of segmenting sensor data, real-time streaming sensor data for tinyML. In particular, how we can make some different choices that are typical these days, potentially save significant CPU cycles and power in your tinyML projects. There we go. Keyword seems to be not my specialty today. So who is Reality AI? We are providing an AI platform that offers machine learning development tools, explainability, and hardware analytics to help you optimize your product designs. We focus on edge AI, primarily in automotive and industrial IoT spaces, but we also partner with companies to develop solutions that include edge AI. Basically, we're a no-code solution combining advanced signal processing and feature discovery with AI that's deployable on inexpensive edge nodes. As we're working with ARM here is a great example. So let's jump into the stuff I'm talking about today. And that is streaming data. What do I mean by streaming data? Just to kind of fix ideas, right? Signals, the continuous streams of digitized data. So audio, vibration, motion, electrical signals, things we can draw as squiggly lines on a graph, right? There may be many channels, there may be one channel, but the point is it's a continuous stream. It's not a discrete event captured in a window or some convenient bite-sized chunk collected every so often. So in order to do machine learning on this stream, what do? We break it into windows, right? Data frames. We're going to consider some window size, and we're going to stride across this incoming data. Probably those windows overlap for those familiar with the process, just in order to avoid losing something between frames or misclassifying something due to an edge effect, right? So what do we do with that window? Well, here is the typical machine learning inference process, just to kind of remind people what's under the hood and set ideas. We're going to take that segmented stream, that signal coming in, it's broken up into analysis windows. We extract features. We apply our favorite machine learning inference mechanism. And if we're careful, we smooth over a few of those events so that we contain any momentary lapses in judgment, things that might be a mistake made momentarily by the machine learning inference. So that's the basic process here. To kind of get a little bit more specific, right, here is something that's become quite popular in the deep learning field, particularly for things like audio, where what are we doing? Well, we're taking our segment, we're going to generate something like a MEL spectrogram, or maybe it's Kepstral, depending on exactly what your application is, right? We're going to run a convolutional neural network across that in order to find interesting time frequency blobs, which are basically our features. That information gets aggregated into a DL inference layer, deep learning inference layer, and we get an output from it. Now, in a way, this is becoming sort of a de facto standard for deep learning audio and some other signal AI. It's very powerful and very general. In fact, it's extremely impressive that it can fit on a small MCU at all. And there's some really smart people working in tinyML to kind of make that happen. But you know what? It's a lot of machinery. It keeps us very busy. If you're running this on a Cortex-M4, you're probably not doing anything else at the same time. There are also simpler machine learning inference algorithms, right? Maybe if we're looking at something like rotating equipment, like machinery in an industrial plant, maybe we do something like just take an FFT, do some peak statistics. I mean, look at the data through an SVM and smooth and get output. It's a bit simpler. We might be able to get much faster inference rates than the full deep learning approach, but you're still going to tend to use as many clock cycles as you let it if you're in continuous mode, because you don't want to miss anything. You've got to look at every single window. So you can work around this with threading, but it still keeps you as busy as you let the machine occupy. So who cares and why? Well, there are a lot of reasons. Two groups, really. Maybe we've got other things to do, right? If the MCU is dedicated to continuous inference, there isn't room to do other things. System functions, GUI inputs, communications. So if you're working on small MCUs, you can just run out of capability. Now, you could add another MCU, right? Okay, that's one approach, but every one of those costs money. And if you're building a product, that increases your BOM cost, and your boss doesn't like that. You want to minimize the hardware cost, minimize the expense going into this. And even if you're on a big system, let's say a Cortex-A7, right? Every busy thread is stealing time from something else. So maybe you just want to make that a choice to use less CPU cycles if you don't need to. Now, in addition, clock cycles cost power, right? The system has less to do. We can lower the power usage. We can drop the clock rate. The ARM Cortex-M series actually has several sleep nodes, as I'm sure some of you guys know better than I, if you're active developers, where you can put the thing to sleep, wake up on an interrupt, service an event, and go back to sleep if there's nothing left to do. That could be a very powerful way of saving money, as you guys well know. And even in and so small devices, they have limited battery life, right? So that's saving us power. Even in bigger systems like a car, we might need to meet a total current budget, right? You can't come back after 2 weeks and have your car battery dead simply because you were listening for vandalism on the outside of it the whole time. And even if you're plugged into the mains power in the wall, you may still, as a manufacturer, want to meet some kind of eco standard for standby power consumption. So that power is actually very salient to our designs. All right, so what are we going to do about this? Well, we're going to look at a two-step architecture. I consider most of what we're talking about today to be sort of a special case of this. the idea is rather than jump to the full machine learning inference immediately, we're going to take that buffered frame that comes in and we're going to add a candidate screening layer on it, right? So as it goes into this candidate screening layer, which hopefully is relatively lightweight, hopefully most of the time we simply reject that as nothing interesting here, move along, and go on to the next buffer. If we get something that's a candidate actual event, then we crank up the full machine learning horsepower and we do inference on it. Perhaps we still reject it, or perhaps we get the confirmed event, but we didn't even wake up the full machine learning inference until we got an event from that first layer. Now, to take advantage of this, the trick is, of course, to make that screening step computationally lightweight while still rejecting as many true negatives as possible, so you spend your time not running the full machine inference. This construction is supported in Reality AI tools, and I'm going to be showing you some examples of how you would begin setting that up in a few minutes. All right, let's talk about energy triggering, right? One of the simplest ways of doing this kind of screening. The idea is not brand new. Wake up on an event. It's a familiar concept in engineering. In fact, many hardware sensors even have a mode where they can kind of sit in a low power state until a certain thing is achieved, maybe a burst of energy on a accelerometer or a embedded mic chip, right? This can generate an input and wake up upstream hardware in order to react to it. Same principle applies to MCUs. You can wake up, you can empty your DMA buffer, do a quick computation, and if there's nothing there, you go back to sleep. Great way of saving power. And again, the Cortex-M series has this built in, and there's lots of designs around that idea. So you can either reduce power, or if you've got other things to do, you can go do other things, not spend all your time doing machine learning inference. There's a lot of use cases for this, right? Obvious things come to mind, things that are distinct events, like in a smart home situation. You've got glass breaks, door opens, dog barks, smoke alarm listening, things that occur and are relatively distinctive from their environment that don't take a lot of horsepower to get candidates and look at. In smart car environments, you've got vandalism detection, micro collisions. In other smart devices, I'm going to show you, in fact, a project with gesture detection in it that uses this exact principle. In machine health, if you're reacting to events or even lack of events, again, these things can trigger the machine learning horsepower only if and when you need it. In a lot of tinyML situations, events are episodic, or on a tight power budget or a tight processing budget. That's the important point here. All right, so if you're going to use this triggered inference, there's a couple things to consider. First of all, as I already said, you need the screening step to be lightweight, quickly computed. Otherwise, you're wasting your time, right? So that's got to be low computational. Ideally, you want to still screen out as many true negatives as feasible without dumping any of your true positives. Because if the true positives don't make it through the screening layer, then they're never going to get classified by the full machine learning inference. So the two layers interact quite significantly. And the full machine learning layer needs to be optimized to make decisions specifically on those candidates that are going to pass screening, not the full world of possible sounds or vibrations or encounter classes. So the training set has got to reflect what the machine learning layer is going to see in deployment. Now, the good news out of this is that it often means that the machine learning layer can be simpler than it would be otherwise, potentially much simpler. Why? Because it's actually dealing with a lot fewer counter classes, a lot less training data has to be considered. Second reason, those windows can be time aligned by the event trigger, which means your feature space computations can be much simplified because you know where the event starts approximately. You don't have to go searching for it in the window. And that actually also reduces your model complexity significantly. Okay, so what kind of things can you trigger on? There's a few simple but powerful options we're going to talk about. Energy dynamics, that's the one that just jumps out, right? Amplitude, or maybe you want to look at the envelope of the signal, RMS, over a brief window. You can do this with fixed or dynamic thresholds. You might want to look at steps in RMS, right? Sometimes you get an increase in energy relative to the background or a dip in level, and that can trigger your inference. We can think of oscilloscope type triggers, things that you're familiar with on your desk scope. Positive and negative threshold crossings, a particular amplitude point. You can take channel sums and differences. You can look at magnitudes, things that are very simple calculations, quick to compute, but can give you good information for making this decision. You can also take out your DC bias, just like hitting the old AC switch on your desktop scope. With a little more computation, we can also do band-limited dynamics, right? We can add in a filter and look at the same energy fluctuations in a specific range of frequencies. And this lets you, of course, ignore background noise that's out of scope simply due to the fact that it's in the wrong frequency range. Again, powerful tool, don't need to turn on the machine learning yet. This energy trigger segmentation mode is in Reality AI tools. And the next thing I'm going to do is, again, show you how we would start using this. So here is a simple case study, honk detection. Our partner in this case wanted to discriminate honking sounds from cars on a factory floor from other noises in the factory, right? What they wanted to do was roll up the car, go beep, beep, to start a test sequence, kick off something that needs to be evaluated on the car without any other additional connections to it. There are other noises in the factory, even though the honk is pretty loud, but there are other loud noises, echoes, distant honks, machinery clanking. So that's the challenge here. We're just using an audio microphone, and the partner was running this on an ARM Cortex-A53, an industrial IoT gateway. That's a lot of horsepower in a sense from a tinyML point of view, but on the other way of looking at it is that box was quite busy doing other things. So they did not want to dedicate a lot of CPU to this little feature they're adding. Just to kind of set the situation up here, here's an example of a few hours of audio recording from the factory floor. Right, what you're seeing here is there's a lot of low-level activity below that 0.05 level, which is the machinery, the processes, the testing going on the line. And then we see these series of higher spikes here. Now, those higher spikes include the honks we're looking for, but they also include machinery noises, squeals, drop wrenches, things like that. And that's our task. We need to discriminate one from the other. Key point here, though, is this is hours of data. And really, if you think about it that way, there's not that many spikes. So there's a lot of time when we can simply do nothing. We can simply, just on the basis of the lack of loud noise, say, nothing to see here. And that's what we're going to capitalize on to make a much more efficient machine learning solution. So let me jump over now to our product, which is Reality AI Tools. This is a slide I'll come back to and kind of give you an overview of other things it does later. But right now I'm going to look at the AI Explorer features for doing AutoML, and in particular, the optimal segmentation to select these energy triggered options and create a candidate detector along with your machine learning model. Switching over to the product here, let me orient you a little bit. All right, right now we are in our product. We're doing a live demo. You can see we're in a project called Horn Honks POC. That's the demo data I've got. We're in the data section of our menu on the curate page. And if I expand this top window here, we can see we have a whole bunch of files. These files are captured recordings from that factory floor I showed you a minute ago. In essence, what we've done is we've captured some examples of honks, the actual target, and some examples of counterclasses. They need to be labeled initially because this is supervised machine learning. And so we've taken those segments and put them in here. And if I open up this metadata tab, we can see that the top section is mostly noise. And as I get toward the bottom, I start seeing, there we go, some honk cases over there, different file names. All right. I am going to open up, I'm going to actually select these files first. And then I will open up our segmentation tool, switch to energy triggered mode, and open up a convenient preview tab that I've got. Now, what comes up initially on the right here, we have our single channel of audio, and we have a trigger channel, which I'll talk about in a second. But right now I'm looking at one of the first noise cases, one of the first counterclasses. And just to kind of make it clearer what's going on, I'm going to jump down to the first of the honk cases. There we go. Now you should be seeing the audio channel, right? And that's beep, beep, right there in front of us. Okay, so the trigger channel right now is set to reflect exactly what's in channel 1. And I'm going to leave it that way, but you'll see it change as I modify some of the settings. So this is the actual data, again, at the bottom. This is the channel that we're operating on for making our decisions. It just helps us visualize it a little bit better. All right, now I know that these are relatively quick honks. So first thing I'm going to do is reduce ourselves to 1/8 of a second window. In fact, that's close enough to 2048. I'm just going to be a purist to make it a power of 2 there. I'm going to get rid of pre-trigger, which I'll talk about in the next section. And I'm going to set a relatively short minimum separation of about 1/16 of a second between these things. And what I will then do is I'm using an amplitude trigger threshold, right? And I'm going to set a threshold looking at this gauge over here of about 1,000. All right, let's see what happens doing a refresh here. And there you go. Okay, so what this is showing me, that orange line, each of those circled points is a trigger event, and each of these blue fields shows the captured window that trigger event generated. So that's what's going to be captured for my machine learning layer to analyze. Now, I don't like this one quite yet. This is audio, so it's sort of easier to see this if I change to looking at the envelope rather than the individual data. So I'm going to change to RMS and set about a 1/4 second window here over which to compute that. Refresh. And what I'm seeing now is the envelope of each of these sound bursts. Very convenient way of setting thresholds. Very simple to compute. Again, we have 1, 2, 3 triggers. The second one is actually a retrigger on the same honk. Now, how do we get rid of that? Because really what we want to do is we want to know when they've got individual sounds. We want to be able to count these. You want to be able to distinguish beep, beep from a single beep or some other combination. All right, so we want to get each and every onset, each and every attack of these envelopes. One thing you could do is just look at positive crossings of the RMS. That can work in a lot of circumstances, though it has a few limitations. A trick I like to use is to shift to what we call RMS step. RMS step is basically the derivative of that window. So when I refresh, what you're now seeing is the moment-to-moment numerical derivative of that RMS, just the step in it, basically. And conveniently, at the beginning of that, we've got some nice sharp peaks because these are very fast attack sounds, the honk honk. So that gives us a good way of screening for these things, again, before we even get into the machine learning part. So if I set a reasonable threshold here, looking at the graph, oops, and go ahead and refresh. All right, now I'm grabbing 2 windows very nicely around each of the horn beeps. That's exactly what I'm after. So this is a reasonable setting for this case. I look at the next set of local honks that I captured for training. Again, I'm getting 1 for each onset occurrence. I'm not actually getting the very beginning of the envelope. I don't really care about that. I just care that I got 1 for each occurrence. Look at the next one. And again, we're capturing neatly the horn honks that we want to analyze with the machine learning itself. Great. We're half done. The other half is our counter classes, right? So now that I've discovered these settings, I'm going to take them over to the counter class data I collected and see how they work there. I'm just going to jump up to the top. These are other noises from the factory floor. If I open one up here, we can see that, there you go. It's actually ignored a lot of it because it didn't meet the criteria. They didn't have fast enough attack to trigger our RMS step mode. I found one example here, which is a counterclass. Some of the other noise segments. Okay, this one also has just one example in it. So if you think about this for a second, we're already screening out all of this other loud sound that we would have had to discriminate in the machine learning classifier directly. So that's potentially going to simplify our classifier. If I look at another one, just to There we go. So here, this one's got a few more classes. So all of these counterclass events, all of these candidates will be included as our alternative class in the classifier, right? As I execute using this particular trigger mode. So that's exactly what we need to train our classifier on. In order to work with this data, I would simply submit it, and give it a list name, and so forth. And that would collect each of the triggered events from all of the files and put them in nice sample lists that we can work with for training purposes and testing purposes as well. Now, I've already done that. So I'm going to close that window and jump down here and open up the list. And you can see that having run across all those files, I've captured 75 examples of honks and about 2,600 counterclass examples. Now, 2,600, okay, that's a lot, but it's a lot less than the number of 1/8 second windows in 5 hours of data. So it's all relative. We've really trimmed down the amount of data that we need to use here. And we've simplified the problem because it's all time aligned. The next step in our typical workflow process is we go over to what we call AI Explorer. I go to the classes section because I'm generating a classifier. And I've already actually executed this previously, so we don't spend time online here. But here's that same list run through. And what the AI Explorer has done is it's examined a large amount of features and models and picked those that work best. Okay, and what you can see down here, hang on a second, I had a note here. Let me make sure we check my my settings here. Yeah, I think we're good. Okay, returning back where we were. What I can see here is I can see the results of our AI Explorer, and you can see that the top answers here are actually doing quite well, right? Using k-fold accuracy as our metric, we're at 100% here. Now that doesn't mean we get 100% in the real world. Obviously, holdout data may do a bit worse, but we're actually doing excellently. And in fact, maybe not unexpectedly, the explanation over here tells us that we are dealing basically with spectral features. Why does that make sense? It makes sense because the horns have a relatively consistent sound to them. And that's a lot of the decision aspect that's being considered here, right? Now, if I look at the complexity of this classifier, it's actually pretty small. I'm doing about 20,000 operations to complete this. And it only takes about 12 kilobytes to describe and store the model. So that's pretty darn tiny from the point of view of running on a Cortex-A53. That's going to be well sub-millisecond inference. Even if I was running on a Cortex-M4 at 80 megahertz, that'd still be probably a millisecond of inference. It's pretty darn tiny. And the reason it's so tiny is because we've reduced the data problem significantly. And again, I remind you that we're not even going to execute that part of the thread until and unless we pass our candidate screening test. So there you go. That's our first one. That's a relatively straightforward application of this to an audio detection problem. I'm now going to jump back to my talk here briefly. Now, what else can we do in Reality AI tools with this? Well, having already found a classifier, we can then take a look at optimizing components, right? We could then try and optimize this classifier to work on particular quality of components. Quality, I mean, let's talk about sample rate, bit depth, things like that, so that you can choose your sensors to minimize your BOM cost. We also have mechanisms for dealing with data. You can check its quality consistent as you acquire data over time. And of course, you can then export your results to a embedded code project. We're going to be able to export code or export an object file that you can load right into your IDE to build your own project around this classifier. And that object code is going to include both a function that does the candidate screener, as well as the function that does the full ML inference. So you can separate those in your process. All right, now let me go on to a second case here before we open things up for questions. And that case is a little bit different. In fact, it's completely different. We're looking at capacitive gesture detection for a home appliance. Let's consider it to be a refrigerator. I can't share everything about what the partner was actually doing, but it's good enough. So the idea is I want to reach my hand forward and I want to have the door know I'm reaching for it and pop open a little bit to make it easy to open before I get there. All right, we're going to do this with a capacitive gesture or a capacitive chip to detect it. We have to deal with a variety of hand sizes, right? Angles of approach, speed, skin dampness, things like that happen around the kitchen. There's a bunch of challenges. We don't want the door to pop open when you're walking by, reaching by it, or leaning against it, or just wiping it down to clean it, once a week. Those would be annoyances, and we want to avoid that. Again, we're working with a 2-channel capacitive sensor. And in this case, the partner wanted to put it on an ARM Cortex-M4. Now, let me emphasize that this M4 was doing multiple functions. Again, they didn't want to spend a whole chip on this feature. This thing is basically run on the fridge. So it needs to do this function on a very compact footback very quickly. All right, let me jump back into Reality AI Tools, and I shall switch to the other project I've got here. That is, there we go, gesture POC data. And I will go back to the curate page of my data section and take a look at my files. I'm going to open up this so I can see it, just resort it so it's convenient. And again, as before, I basically have a bunch of examples here. I have a number of positive class examples, recordings of various people of various sizes and shapes reaching for that door. And I have a lot of the counter classes, walking by, scrubbing the door, and that sort of thing. If I open up my metadata here on the side, I can see how these files are labeled. So the reach case is the positive case. The counter classes are all just labeled counter class. It's just really a 2-class classifier ultimately. As before, I'm going to select these source files. I am going to go to my segmentation tool, switch to energy triggered mode, and open the preview. And now what you're seeing here, it's a little bit different. First of all, there's multiple channels of data, right? So channel 1, 2, 3. Before we just saw one channel of audio. Now in this case, I've got 2 channels of actual capacitance. This third channel is actually a computed difference channel that we found to be useful during the development. Each one of these little spikes you're seeing here is actually the gesture. That's the capacitive reaction to a hand coming in, repeat, hand coming in, and so forth. Now, I would point out that this is data collection, and this actually includes more than just the gesture we want, right? We want the reaching forward part, not the pulling the hand back part. So we're going to have to capture just the part of the waveform that we're after. So what I'm going to do differently now this time is, first of all, I'm going to adjust the pre-trigger to get rid of part of the window. I'm actually going to set up a combination of channels feeding the trigger channel. And I'm also going to then remove some of this bias drift here. So let me just take it a step at a time, right? First thing is channel 1 and channel 2 should be treated equally. We don't want the door to open only if you're a tall person reaching from the top, right? Any angle is fine. So in order to consider these channels equally, I'm going to redefine the input to my trigger channel as a vector magnitude of those first 2 channels. All right, so when I refresh now, the top is now displaying, it looks very similar because of the way the math works out, but in fact, it's now combining these 2 data channels as a vector magnitude, and that's reflected here in the trigger channel. We're still using an amplitude trigger, and nothing, it's quite simple. The next step here is to get rid of this bias drift. This capacitive sensor, as you can see, it does not maintain a baseline value of completely consistency, depending on the weather, the moisture, the dust, whatever it is touching that that refrigerator, that capacitance can vary up and down sort of randomly. And that's a pain in the rear end for setting a consistent level here. But we can get rid of that very easily by turning pre-processing on. Again, this is akin to hitting the AC switch on your desktop scope, only better because there's a lot more possibilities. I can do a dmin over a range of data, and when I refresh, we see immediately that we now have a much smoother baseline. Everything's now zero reference, so it makes it easy to set a threshold. And in fact, if you look at what we're capturing, we're already pretty close to capturing exactly what we want. If I zoom in a little bit, these initial settings are doing a good job. Now, it's not exactly right yet. I'm getting too much of the downslope. I just want this upslope part, right? That's the reaching in part of the gesture. So in order to capture that, I'm going to shrink this window just a little bit, and I'm going to adjust the pre-trigger. Now, if you've worked with desktop scopes, that word means something to you, but in case you haven't, all that does is set the point at which we capture a window relative to that trigger. So the trigger point's here, but the window starts here. Now, are we going back in time? No, we're just keeping a buffer, right? So we'll look back in the buffer and grab the window a few points back in time from when the actual trigger happens. I'm going to set that to about 20 and then refresh everything. And now we see that we're pretty neatly capturing the beginning, the reaching in portion of the gestures. It's not perfect, right? But it doesn't have to be perfect. You have machine learning in the second stage, so it could do some work, right? It's pretty good. There's going to be a little bit of variation, but that's going to be accommodated by the machine learning layer. And so that is our training set for the positive class. Again, if I look at another one of these example finals for the positive class, again, we're capturing the beginnings, the reaching in gesture on each and every one of these gestures. Great. Now, what does that do on the counter class? Remember, we have to capture both positive class and negative class for the second stage of the detector, right? If I jump down to the noise cases, I happen to know that the low noise cases are basically the simpler cases like leaning on the fridge or walking by. And in fact, that is not generating anything like the same curve. We've ruled this out entirely. We don't even need to collect this data and put it into our classifier because it's never going to be seen by the classifier in real life. If I look at another one, again, same deal. Didn't trigger at all. That's great. I'm reducing my data space substantially. Now, if I go toward the bottom here, these are the more challenging cases like wiping down the fridge. Okay, here I do see some different looking gesture or type pulses, some of which actually meet our criteria. So these now become our counter class data. That's what we're going to train against. If I go to another one, just to make sure you're getting the idea here. So here we go. Again, many of them are eliminated, but we do have some to train against. All right. As before, I'm going to generate a list, and I will trade upon that list to build a classifier. So captured list is here. Already done. And you can see that using the criteria I've just set, I've collected 640 examples of that reach gesture and 1,500 examples of counter classes. I might do a few more if I'm using this to build a real product. That's a really good starting point for this level of classifier. Again, I go to the AI Explorer, and I would have run this to explore feature spaces and classifier models in an automatic fashion. And I can see my set of results here. Again, pretty darn good as judged by k-fold accuracy. It's not quite 100% this time, but in fact, we could use other portions of tools to adjust that and improve that. And that workflow is not part of today's talk, but it's actually addressable. If I look at the explanation of this particular classifier, the one that is just distinguishing the reaches from the other breakthrough candidates, it's actually pretty simple. This is using effectively parametric statistics on those few data points, and that's a tiny computation, right? So because we made the data so simple, it's easy to distinguish A from B. If I look at my complexity over here, I'm talking about under 1,000 operations to complete this, right? And about 660 bytes is the total parameter space. So that is truly a tiny classifier. You know, 1,000 operations. I mean, on an M4 at 80 megahertz, right? We're even there. We're sub-millisecond. That's great. And in fact, the screening to go into this is probably under 100 operations. So that's even smaller. So this can be set up to really work quite fast. It only wakes up when we have a candidate, and then it runs this, and even that inference doesn't take a lot of time, so that processor can be busy running the fridge the rest of the time, really with very little interference to its normal operation, just to add this feature. So that's what we're about here. That's why we're doing it, and that's pretty much the bottom line on this demonstration. I am now going to switch back to the slides here, and just again to remind you how would we use this for real, right? You're going to load your streaming data. You're going to use our segmenting tool in the energy triggering modes, selecting some of those basic methods that I've just demonstrated to you. And then you'll do an AI Explorer to find the best features and the best model. You can deploy that right to code that you can load up into your IDE and embed in your project. So that's the bottom line. Again, it's thinking a little bit differently than has become common these days, but we think it's a pretty powerful way to do things, you know, when you don't need full bore continuous monitoring, and it saves you a lot of CPU cycles, potentially a lot of power in your products. Thank you for listening to me, and I'd be happy to open us up to questions now.
Thanks so much, Jeff. Great presentation, fantastic talk, and you know, it's great to have I always love a demo. Maybe I'm biased, but I do love a live demo of these things, and the demo got shown. Everything worked brilliantly, so all good. And as I said at the start of the talk, get your questions in. Please use the Q&A box. I've got a couple on my side, actually. So in terms of the kind of ARM IP you support and kind of ARM targets you can deploy to, do you mind just going through, just telling our audience a bit about that and kind of what you support on the ARM side?
Sure. Actually, pretty much your full range. Anything using the same sys library, we can support, and that we can compile object code directly for the microcontrollers. We can also compile to a Linux build, for example, if you're running on something, you know, like a Cortex-M chip with more of an operating system behind it.
Awesome. Yeah. That's what we like to hear. Everything. That's great. Let's get you on everything. Absolutely. That's great to hear. And what's also great is you guys did a tech talk last year as well. So for anyone who missed that, I'll paste the link in the chat in a second. But do you mind just kind of explaining what you talked about last year in the prior talk, and kind of a bit more of an overview on that side as well?
Sure. Last year, my partner Stuart did a talk describing kind of more of the general workflow of Reality AI tools. You know, so if you want to see how you might go about to use those tools, including data readiness, including setting up your data, building auto ML models, and doing optimization for your BOM, you can take a look at that talk. It shows you kind of more of a big picture view of how to apply this to building an actual product end to end.
I've just pasted in the chat, so yeah, do go and check that one out. It was a great talk last year. It's great to have you guys back for a second time. So you know, it's great to have that. I'll turn to the a couple of Zoom questions we've had. One of which we did answer in the chat, but I don't think everyone saw it. Was from Pratik, was around, is the software, I'll take the first part of his question, or your question, is the software free to use? I believe, Stuart, you answered that in the chat regarding the subscription model. Do you want to just, or yourself or Jeff, do you want to take that one, just explain a bit more about the kind of business model and accessing the software?
Go ahead, Stuart.
Yeah, sure. So Reality AI software is sold on a subscription model, and we work with corporate R&D and factory operations technology groups around the world.
Awesome. So if they're interested, I guess, get in touch with you guys using the, do you want to using the email?
Yep, just get in touch with us using the contact information that's up on your screen right now if you're interested in learning more.
So go do that, definitely. And yeah, as I say, do check out their tech talk from last time. Recording from today, in case you missed it at the start of this talk, the recording from today and the slides will all be live on our website and our YouTube channel within the next 24 hours or so. And then the second part of Pratik's question is, how can we see the algorithms used for baseline removal or segmentation?
So the algorithms are exported as part of our what's delivered when if you bring it out to an IDE. So they're usually very straightforward. Stuart can add some color if he needs to about the cases in which we share code or don't code, but they're very straightforward. We just automatically generate them.
Yeah,
and
basically you can get full transparency on the computations looking at the underlying code, and we have several options for how you get that. We can generate C, we can generate MATLAB. Take your pick depending on which options you select in the software.
Fantastic, thank you guys. And Pratik, I hope that answers your question. Do put in the Q&A if you've got anything as a follow-up. We've got the guys on the call here. So let's crack on and look at Dave Rogers' question. Thanks for your question. Does the model training benefit from event discrimination for better accuracy? I.e., does the workflow eliminate counter-class examples that would not pass the discrimination test prior to training the model?
Excellent question. And the answer is yes, absolutely it benefits from it. Now, it benefits from it perhaps in a more indirect way than you're thinking, because simply having reduced the space in which we're making a decision, we're getting rid of a lot of counter classes, right? So we're not going to end up with the same model that you would have generated if you'd had exposed it to everything in the world. That's true. But that model probably would have had lower accuracy because it's so complicated. So yes, the answer is yes. This is throwing away the things that are never going to matter, building a simple, highly accurate model that's very tight. That's exactly what we're after.
Fantastic. And Dave, I hope that answers your question. Again, with any of these, do feel free to follow up with now or with the guys offline if you've got any questions, and contact Reality using the stuff there. We've had a question come in here saying, I'm very impressed by the very small cycle and memory consumption of the gesture detection demo. Can you share what ML models or mechanism are used after the data segmentation? Thanks.
Sure, don't mind. We're basically using an SVM in that case. So it's very fast to compute.
Awesome. So that's the question we've got in for now. Do get your question. Oh, no, just literally as I say that, I've got another one come in, and do get your questions in. We've got about 5 minutes or so. So make sure you get your questions in. This is the last chance you'll have in today's talk. So do get them in the next 5-10 minutes or so. Question in from Pratik again. Do we have a model size reduction feature by removing sparsity from the model?
Yes, the AutoML itself actually tries to make some of those optimizations initially, but then there's some other steps that can be taken within tools to further reduce features. You can actually explore the significance of sub-features, for example, and then eliminate the ones that don't matter very much.
Awesome. Thank you for that, Jeff. So yeah, do get your questions in. We've got a few more minutes to get those in. We'd love to hear from you. I've got another question as well on my side. Have you guys done any sort of direct comparisons with using a convolutional neural network, CNN, DL type audio inference model?
Sure, that's a great question. And it's yes and no. We've built not these specific classifiers that I showed you today, but using that same architecture, we've certainly dealt with similar things, right? Simple audio events that are comparable to honk detection. And on a Cortex-M4, for example, you're seeing inference times north of 150 milliseconds or more, because there's a lot of machinery running to execute those models. Whereas we're at a few milliseconds by the time we do this, maybe add some smoothing. And again, that's because it's just a much simpler model that you're able to use.
Awesome. Thanks for that, Jeff. And we've had a follow-up question on SVM come in. Is it linear SVM? And the second part to it, is the SVM implementation provided by ARM? I'm not sure on the second part of the question. I'm afraid I can't answer that directly, but do you have any further comments on the SVM side of things on your side, Jeff?
I actually would have to look at this one specifically, but I'm fairly certain it's a linear SVM. It's a very straightforward problem once we break it down the way we broke it. And no, we actually have our own optimized code for doing the SVM implementations. I know that ARM is providing a number of machine learning toolboxes themselves now, but we have our own code in this particular case.
Yeah, and let me just add that Reality AI Tools supports a variety of model constructions and learner algorithms and that type of thing. So that's a longer conversation probably for a different day.
Absolutely. We'll get you guys back another time. No, absolutely. Great questions all coming in, and please do keep them coming in. I mean, Jeff, while we're waiting for the last couple of questions, is there anything else you'd like to add on top of the talk today? Any kind of catch-all or anything you wanted to add further from today's talk that you kind of wanted to go into a bit more detail, maybe that you haven't had time to? Or anything else?
Well, sure. One thing I didn't actually mention during the talk, although it was on one of my bullet points, is we have also used this same thing just for data labeling problems, where you're not necessarily jumping straight to doing a classifier, right? So if you've got a bunch of very short sounds in a long recording that are going to be just a pain in the butt to try and label by hand to mark, you can use this energy triggering to automatically capture those. And in fact, you can then, again, didn't show you this in the actual demonstration here, but once you generate that list in segmentation, it's possible to export a CSV file showing exactly the start and end points of each captured event. So, even if you're not jumping, as I said, all the way to building your classifier, it's a nice little handy data labeling tool in some cases.
Definitely, absolutely agree. And it's great to see you guys talk about this. We're really thrilled to have you guys talking again at these tech talks. So, let's see. We've got another question come in. How does this type of model work and perform with image or video data? Could the model really benefit this data?
Sure, fair question. And the answer is it doesn't at this point, because we don't do images. We specialize in signals, and that's exactly what we focus on. I think I could think of some related ways of applying this there, but that's not our main thrust. Gotcha.
Thanks for that, Jeff. And yeah, great questions coming in. Last chance to get them in before we wrap up. As I say, everything from today is going to be goes on our recording, part of the YouTube channel, ARM Software Dev YouTube channel. So make sure you're subscribed to that, and you'll not miss our future talks from our partners and from the ARM ecosystem, and from speakers from ARM as well. And the slides will go on the developer.arm.com/tech talk page. That was linked to in the slide. So do check those out, and it's linked to in the chat as well. So do check those out, and loads of prior talks as well. So if this has kind of sparked your interest in AI/ML, if you're new to it, you're just getting started with it, or you've got a lot of experience in AI/ML, this is the place to be. There's a ton of resources out there. So to do check out our series. So I think we are pretty much at time. Jeff, Stuart, any final words of wrap up before I close from your side?
Again, thanks for having us, Tobias. It's fun to talk about this stuff. I enjoy doing it, and I love it when people will get to use it, frankly.
ARM's a great partner, and so many of our customers are deploying to Silicon featuring ARM IP, and it's just great to be on this series with you again. Thank you.
It's great to have you guys, and thanks so much for that. No, it's great to hear that so many of your customers deploying to ARM. It's what we love to hear, and it's great to work with you guys as an AI ecosystem partner, and I'm sure we're doing more together over the next few years. So do keep an eye out for that, and do keep an eye out for our next Tech Talks, everyone. So thanks for joining. Make sure you, as I say, check out our YouTube channel, get subscribed to that so you don't miss any of our upcoming talks. Sign up for our next Tech Talk. There's a bunch coming up, really, really interesting topics that aren't even mentioned on the pages that we've got coming up for the rest of this year. All around different areas of AI and ML, and it's really, really exciting. So on behalf of myself and the ARM team, and Jeff, Stuart, and the Reality AI team, thank you so much for your time today, for joining us for our ARM AI Tech Talk, and we'll look forward to seeing you again in 2 weeks' time. Thanks very much, everyone.